Again. Now I'm going to talk only science, and it's really a pleasure for me, as you see, the title has been changed. It's a pleasure for me to describe this collaboration. Really, the collaboration with Northwestern, with the group of Lincoln and David, have really dominated my scientific activity during the last 5 or 6 years. And also, I will not talk about this, but this David described in his talk. So what I'll describe you today is maybe 2 or 3 parts. Wires that are grown via VLS in Lincoln's lab. This I call bottom-up, not only me, the community. And then wires that are grown top-down. There are many applications of nanowires, and I don't have to describe them to the people now here. There are more experts than me. But one important application, which I will come back to in the end, is sensors. Nanowires can be very efficient or very sensitive chemical or biosensors, and I'll come back to this in the end. The bottom-up technique, the most common bottom-up technique, and this is from Lincoln's lab, is the VLS. When you put a gold catalyst and you grow the nanowire vertically like a mushroom inside a CVD reactor. An important issue here is the distribution of dopants. The electrical properties of nanowires are dominated by dopants, and if you want to have a control device or a control p-n junction, you need to control the dopant concentration. And you can see here immediately that in this configuration, you have inhomogeneous dopant concentration along the wire just due to the mushroom growth, and also very inhomogeneous radial distribution. I'll just go over this briefly. This is not the subject of the talk. Me and Lincoln and David have worked on this during the first BSF. And this is in opposite to the top-down approach. The top-down approach is like Intel is similar to what Intel is doing. They are basically etching a silicon to a nanowire-like shape. And by the way, it is not been announced officially, but only unofficially, because Intel doesn't like official announcement. Intel is most probably going to establish a 10-nanometer fab in Israel, in the south of Israel. Intel has never announced it, but it has been announced in the press. So this is a very, very good, if it will indeed happen, this is very good for Israel's science and technology. So, as I said, one of the major problems in nanowires is how to control the dopant distribution and how to form good, and good mean abrupt electrical junctions. So one very good tool to measure it is a scanning probe method. As you know, my group has been involved in Kelvin probe force microscopy since I came here in 1996. And this is a very useful tool for measuring nanowires, as I'll show you during this talk. The principle of Kelvin probe force microscopy is based on the macroscopic Kelvin probe. You basically have a tip and a sample. When you connect them, the Fermi level is you equalize the Fermi level. This forms a built-in potential between the tip and the sample. It's like a capacitor. This potential equals the contact potential difference, or as we mark it, VCPD. And by a feedback voltage, you equalize the local vacuum level or discharge this capacitor. And by the feedback voltage needed to do this, you can measure the contact potential difference or the work function. If the work function of the tip is known, you can measure the work function of the sample. A slight disadvantage relative to STM that David described earlier and that Mark Hersam knows very well is the lateral resolution. The lateral resolution, depending when you're working on ultra-high vacuum or in nitrogen like we work, it's around 20 nanometers, few nanometers in ultra-high vacuum. But for our study, this is not a big issue. So I'll just summarize what we have done since 2009. And the big issue that we worked with is how to measure the radial dopant distribution. So we fabricate backgated silicon transistor, where this is the channel of the transistor. So we start with a forest like this. And this is the end device that we fabricate here. And a good method that Elad Koren, the PhD student that started this work, is now in IBM Zurich, was he devised a method how to measure the radial dopant distribution, a very clever method by which you etch successively the nanowire, form steps, as I will show you here. it looks very simple on the slide. It takes some time to do this in a careful way. And basically, when you form this structure here, when you form these steps, you come with a KPFM tip and measure these steps, measure the potential distribution along these steps. And if there are more dopants inside the nanowire if there are more dopants outside the circumference on the surface of the nanowire and less dopants inside, when you form this staircase structure, the Fermi level and the conduction band minimum will look like this, where you have more dopants on the circumference and less dopants inside. We did a lot of simulations and a lot of measurements. I'll just show you the end result. The end results that we end up with a very high inhomogeneous distribution of dopants like this. So you see that going 30 nanometers into the nanowire, this is the middle of the nanowire, the dopant distribution decreases by almost 2 orders of magnitude. There are ways to overcome it. You can anneal the wire, grow them in a different atmosphere. But this was a nice demonstration of the technique and of the inhomogeneity. Just to give you the end result of this whole study, just recently not published, and this is the work of Ido Amit, who replaced Elad Koren, and we were able to show, this is unpublished results, we were able to show just recently that you can, even that you have inhomogeneous dopant distribution, you can form, without, I'm not going into details here because this is unfinished, you can form fairly abrupt p-n junctions. This is a p-n junction in such a wire that was grown in Lincoln's lab. And this is really, you can really form an abrupt junction. And if you want to hear more details, this is in the break because this is preliminary. And now I'm going to switch gear to what I call top-down nanowires. And this is in collaboration with what was Micron technology that was purchased by Intel and enabled them to establish the 10 nanometer fab that is going to be in Micron now. And in this study, we've measured polycrystalline top-down grown nanowires. Why polysilicon? Polysilicon is cheap, but the big problem that, as you will see now, it has grain boundaries. And the grain boundaries, in some cases, has a large disadvantage. But the message is this is a low-cost technique and can be done very easily in a fab. So the idea is to form to deposit amorphous silicon. I will not go over all the steps. And by etching it in a careful way, you can form these nanowires that go vertically into the board, and you can have very easily arrays of nanowires. So what you see here, this is called the spacer technique. So what you have here is the silicon dioxide, and two, we call them ears, like ears, on 2 sides of each spacer, where you have 2 silicon nanowires, and you can form very large arrays of such nanowires. This is how it looks in a SCM. So this is an array of 2, 4, 6, 10 nanowires. 10 spacers, and on each 2 sides you have 2 nanowires, one here and one here. So you have 20 here, and they can be very easily measured by the Kelvin probe force microscopy. What do we wanted to measure? We wanted to measure the active dopant distribution and actually the effect of the grain boundaries on the electrical properties of these wires. This was the main motivation. So the Kelvin probe force microscopy is a very good technique for it. And what you see here is a measure of one wire. I'll show you in the next slide, is a measurement, a KPFM and topography measurement along here, along a single nanowire. So if you look carefully, this is the topography, and in the topography you don't see a nanowire very clearly. Why? Because you measure the topography across here, and you cannot distinguish the nanowire very clearly from the silicon oxide spacer. But if you measure the contact potential difference, since the work function is different, you clearly can distinguish the nanowire. And if you apply bias on the 2 sides of the nanowire, you apply bias here on the other side, on the 2 contacts, you can gain important information insight on the electrical properties of the nanowires. I will not go into all the details, but what we did, we applied biases between the 2 pads, and we obtained the profile along the nanowire, and by fitting it to a solution of the Poisson equation, we were able to get the interface state density in the grain boundaries of this polysilicon grains. So the end result just show you the end result due to the lack of time. And again, I can elaborate whenever you want after the talk. So the end result of this fit, and we think this is a very good solution to this fit. Actually, again, this is applied different biases on the nanowire devices. The end results that we were able, this is in a 90 degrees rotation, the band gap of the polysilicon nanowires. We were able to get the interface state concentration and distribution and the grain boundaries, assuming there are no such states inside the grains. So you see we have a well-behaved, or what is reported in the literature for polysilicon nanowires. Another important fact here that there is a large, because of the carrier trapping in the boundaries, you have a very large difference between the doping density and the free electron density, because inside the grains, the electrons are trapped at the grain boundaries, and they reduce the carrier density by almost more than 2 orders of magnitude. So one important message here, if you want to have good electrical devices based on polysilicon nanowires, you need to have the dopant density above 10 to the 19. So you need the dopant density to be higher than the grain boundary interface state density in order to have good electrical properties. So after this study, we went further on, and with a master's student called Asaf Shamir, we wanted to measure the individual grain boundaries. I didn't emphasize, but this study was based on the macroscopic or average Kelvin probe measurement. And here we went one step further and measured the potential profile along the grain. So each time you see, so I'll slow down a little bit, the black is topography, and the red is the surface potential. You might think that this is an artifact, but I'll prove you in a second that it is not. And here you see a fit to the surface potential. The red is exactly this surface potential measurement, and the black is a fit, a solution of the Poisson equation to this problem. And by fitting this, and this, we think that this is a fairly good fit, we can obtain the individual interface state concentration at the boundaries. And it turns out to be about 5 or 6 times 10 to the 12 states, occupied states per square centimeters at the grain boundaries, and this traps a lot of carriers. I will not elaborate on the simulation, but just to say that in the simulation, we included the exact topography of the grain boundaries. This was very important, just to prove you that this is not an artifact. This is the result for an N-type polysilicon nanowire, and this is a result for a P-type nanowire. So you see that this is not an artifact of the topography. And in the end, we have, after measuring many, many grain boundaries and many, many grains, we came out with the statistics of the potential barrier height of the grain boundary of this height. This is the height between 2 grains, the potential height between 2 grains as a function of the grain size. By measuring many, many grains and solving the Poisson equation, we came out with these statistics, and this is an analytical solution to the 3-dimensional Poisson equation. You see that it agrees fairly well with the measurements. So as you see, as the grains become very small as expected, because you don't have a space charge region, the barrier height becomes very, very small. So this is the first part of the talk. The second part of the talk, or the last third part of the talk, will be on a new topic that we are very enthusiastic of, and this is called another top-down paradigm for nanowires, but now we call it electrostatically formed nanowires, a different kind of nanowires, as you will see in a second, and we are very excited about this due to several applications. So what is the idea? I am going back to sensors because one of the applications of this technology is very sensitive gas or biosensors. This is a very famous work that many people cite of Heath from, I think he was then in UCLA, but I'm not sure. Heath that demonstrated that with bottom-up nanowires, you can detect very sensitively NO2 with nanowire arrays. But the big disadvantage, although very sensitive, the disadvantage of this technique, that this is not compatible with the CMOS industry or with the semiconductor industry. And we came up with an idea of how to make a thing that we can mass produce. So what is the idea? The idea is a combination of a JFET and a MOSFET. So we start with a regular transistor. Here you have a source and a drain. And the important addition that we add two side gates called GJ1 and GJ2. And very simple to describe what we do with these two side gates, we just applied, if you look carefully, we have here P plus and P plus, two diodes. You'll see it better in the next slide. So you have two diodes back to back. So basically we apply negative reverse bias on these two diodes, and we shrink the carriers. The depleted regions extend, and we shrink the carriers to a nanowire-like shape, exactly to a nanowire. You'll see it in a second. And if I do a cross-section in this device, I cross-section it in the middle, look on this, ignore these two, we form this kind of nanowire. And why this is close to the top dielectric? Because we have a backgate here. And also the doping profile inside this N region, this is the depleted N region, the doping profile to this, in this direction, the z-axis, we planned it so that we will have such carriers confined here to the top. So we end up with a kind of a virtual, if you want, nanowire or electrostatic nanowire, with a big advantage that this can be manufactured in a real fab and doesn't have the disadvantages of VLS-grown nanowires. So if I compare, for example, such a sensor to this sensor, there are many advantages to this one, as long as it can be as sensitive as this approach. And this is what I'll try to prove you in this talk, and we are continuing the research. So just what we think are the advantages. First, the big advantage is the definition is post-fabrication. We can define the nanowire shape and size after we fabricate it. So we have flexibility. We can tune the size. If we want an unsensitive detector or a very large dynamic range, and I'll show you, we can do a very large nanowire. If we want a very sensitive sensor, we make it very small. It has homogeneous dopant distribution because this is bulk silicon. Increased carrier mobility, again, because it has a perfect passivation here at the top. It has a perfect passivation, not like here. These nanowires are very difficult to passivate. Reduced surface states and 1/f noise and other advantages. So this is the second generation of the devices. All the devices are produced in Tower Jazz. This is a fab in the northern part of Israel. So this is fairly large. You can see the scale here simply because we want to test it in the lab and to work with big pads. This is the pads of the side gates and to work with probes. And the channel is only here. And these are the two side gates, the contact to the two side gates. And what we can do very nicely is to measure this confinement of carriers or this reduced dimension of the nanowires by the KPFM. What you see here is a cartoon, and these are real measurements of the potential profile from source to drain. These are measurements, KPFM measurements. When we have no bias applied to the side gate, so this is a large nanowire. When we have a slightly negative voltage, so the nanowire is decreased. You see the depletion regions extend on both sides. And when we have a really closed channel, a pinch-off, and we can really see it nicely with a KPFM. So this is a big advantage. You have to remember that I don't measure here the carrier distribution. I want to emphasize that I measure the potential profile. So what I really measure, if I go back to here, what we really measure is this. From a top view, we measure this. We don't measure the carrier distribution. So by measuring this and fitting it to a calculation, we can obtain the virtual nanowire carrier distribution and concentration. This is the idea. And even nicer, this is a measurement, and you compare it to a textbook. This is very nice to show to a student. This is a JFET from a textbook, and this is really looks similar to our measurement. This is a measurement. This is not a cartoon. So this is under pinch-off conditions because you have a source and a drain with a 1 volt difference. But this is just for something that I like to show the students. Now to gas sensing. So the first gas that we wanted to sense is very simple, is ethanol, because ethanol is non-poisonous and very easy to measure. And what you see here is the ethanol concentration on the x-axis and the sensitivity, which is delta I over the background current, as we reduce the virtual nanowire dimension by the negative side gate voltages. So in this specific device, we started with a fairly small nanowire. It's a half a cylinder due to the backgate and due to the doping profile. So we start with a half a cylinder going into the board, and we shrink it down, in this case, to 60 nanometers. How do we know? By simulation and calculating the IV. I don't have time to describe you all the details. So you see that by shrinking down, by making the wire small, we increase the sensitivity by almost 1 order of magnitude. Why this is so? Because if the wire is smaller, a single ethanol or a few ethanol molecules have a larger effect on the current flow, like a big river that you throw a stone in, or a very small river that a small stone blocks the flow of water. This is what we think at the moment. There may be other electrostatic explanations, but I will not elaborate on them now. So this was ethanol very simply. Another important advantage of this device is the stability and the robustness of this device. What you see here, the green curve is the IV curve before sensing. This is after sensing of, I think, 70 ppm of ethanol, and after we regenerated with a gentle heating to 50 degrees, the curve comes exactly back to the original one. This is very important and fairly hard to achieve with conventional nanowires. And another advantage I don't show you because this is boring, we measure these same devices for weeks after weeks, and after heating or after some annealing, they always come back to the same behavior. And this is, if you want to do something, not saying industrial, but if you want to do something on the way to be a commercial product, this is a key feature. Another very interesting thing is that we can emulate the effect of a charged molecule by a tip. We did a series of scanning gate microscopy. So instead of a charged molecule, we can come with a charged tip or tip with an applied bias and calculate the sensitivity of the devices. So by comparing the source drain current to simulations, we came out with a sensitivity of less than a single charge. What is shown here is the source drain current of such a device. Of this, you see, we apply source drain current vertical to the board through this nanowire and apply a tip gate bias and measure the change in the current. So each time we apply a step of 50 millivolts, we see a change in the current, which is above the noise. And by comparing this to a model, we came out with a sensitivity, which what we call limit of detection, or fundamental limit of detection. This device can be as sensitive up to less than a single charge, 0.09 of an elementary charge. So it can be a very, very sensitive device. This is what we believe, and we can show that we can improve this sensitivity by signal processing, amplifying the signal, or using other dielectrics. This is just the beginning. So just to end my talk, we demonstrated sensitivity to other gases, and the idea that we have in the moment to fabricate an array. It's very easy to fabricate arrays of such nanowires, and to demonstrate the concept of electronic noise. I see that Noam is standing, so I will not elaborate on this, but basically is to have a signature of a gas, for example, ethanol, as a function of the electrical parameters of the device, and we are on the way. I cannot show you all the details. So this is where we stand now with the virtual or the electrostatic nanowire. So what I've described you in the beginning very briefly, because this was the beginning of the collaboration between me, Lincoln, and David. We have worked a lot on dopant demonstration, and we've just demonstrated in the last few months that we can really, with a VLS technology or method, you can really form an abrupt p-n junctions, and this is a very good message. I don't know if Lincoln will talk about it. I don't know if this technology will come to be an industrial one, but this is very important that you can really form abrupt junctions in this technology. Then I've shown you some work on what I call top-down nanowires, polysilicon nanowires. The big problem with them is that you have grain boundaries and they trap the charge. So in order to use them as efficient electrical devices, you need to start with a high doping level. And in the last part of the talk, our new paradigm, which I call EFN nanowires, we think that this is a concept that might one day, in 2 or 3 years, be if it's successful, may lead to some commercial developments, not only in sensing, also in other applications which I'm not allowed to talk to. So again, I want to acknowledge especially the colleagues from Northwestern, and thank you again for coming here, and thank you especially David and Lincoln for making my last 8 years very enjoyable, both scientifically and to come to Northwestern every year, especially in the summer. It's very enjoyable. And all the funding agency, I thank you for your list, for your attention. I'll be happy to answer some questions. Okay, the KPFM measurements, all at room temperature. Of the detector? Yeah, I haven't shown it, but we have time traces of the, yeah, certainly. And if you want to know the time, constant? Depending on the concentration. As the concentration is higher, the response is faster. It's seconds. Seconds for high concentration of ethanol, tens of seconds for very low concentration. The recovery is only after annealing, after we heat it to 50 degrees. Probably the same, similar time constants. After the ethanol is absorbed, you need to desorb the ethanol, yeah. So, but 50 degrees, this can be done in situ within the transistor. I mean, this is the idea, and we are working on this now.
SOI for the nanowires?
Yeah, SOI wafers, yeah. We have not tried it. I mean, I don't know if people have done, but they might be more sensitive. An important difference is that with the FinFET, the production is very, very expensive. The production of these nanowires is done with a very, very cheap, in a very cheap fab, and not a 22 nanometer node technology, but 400, because you make the channel very large and you just reduce it electrostatically. The FinFETs might be more sensitive. Yeah, but the problem with Intel in Israel, it's a copy exact fab. They don't do any collaboration with research. Actually, Intel is interested in this project, and not from the FinFET point of view, but from our approach. But it doesn't mean that the FinFET FinFET might be better. You mean that in the different grain boundaries? No, for the simulations that I've shown, we have assumed that all the grain boundaries are the same. We didn't go up to this level. It was difficult enough, but we assumed that all the grain boundaries are the same. The problem is that we don't have good TM data for the individual boundaries to see the difference between them. This was the problem, and the fact that Micron was purchased by Intel, and they immediately shut down this collaboration. They don't want to hear it. And he's here, Amit. Where is he? Yeah. Ah, okay. Which one? The EFN? Exactly. Okay, thank you for the question. So the gas is absorbed on the silicon oxide. So it's but the silicon oxide, I was too fast. The silicon oxide or other dielectric is very thin, between 2 to 5 nanometers. So the main point of having this this dielectric is to passivate the silicon. If you don't do it like in the silicon nanowires, if you don't passivate the surface states, you'll have you will not have a sensitive detector like here. Here it's very difficult to passivate all the facets of the nanowire. So even though we have an oxide, adsorption on the oxide, and we show it by simulations. These simulations here, the simulations that we can see single charge here, this is done, these simulations are done with an oxide on top. So of course, if we remove the oxide, we'll have a higher electrostatic sensitivity, but then we'll have a problem of surface states.
So if so, can you say Yossi again?
Thank you.